Have you ever seen a movie where a spaceship jumps into a glowing tunnel and instantly appears on the other side of the galaxy? That's a wormhole. Science fiction loves them because they are the ultimate cosmic shortcut. They let heroes travel vast distances in the blink of an eye, skipping all the boring, long parts of space travel. We see them in movies like Interstellar and shows like Star Trek. But what if I told you that scientists are also super interested in wormholes? It's not just for movies. Real scientists like Albert Einstein thought about them a long time ago. For scientists, wormholes are a fascinating puzzle that comes from our best theories about how the universe works. Recently, a team of researchers did something incredible. They used a quantum computer to simulate a baby wormhole. This experiment brings the wild idea of a wormhole out of science fiction and into a place where we can actually study it. Get ready to dive into a world where mind-bending theories meet cutting-edge technology. To understand what scientists did, we first need to understand what a wormhole is. Imagine the universe as a giant sheet of paper. You're an ant on one side, and you want to reach a crumb on the other. Normally you'd walk across, but a wormhole is like folding the paper so both points touch, then poking a hole through. This idea comes from Einstein's theory of general relativity, where space and time are woven together as space-time. Massive objects bend this fabric, and a wormhole is a theoretical tunnel connecting two distant points. But here's the catch. We've never seen a real wormhole. They're completely theoretical and likely unstable. To keep one open, you'd need exotic matter with negative energy. Something we're not sure exists. So, scientists can't find or build a real wormhole. That's why they turn to simulations. If you can't study the real thing, you build a model and see how it behaves. Enter the quantum computer. So, how do you build a wormhole if you can't actually bend space and time? You use a quantum computer. Regular computers use bits, ones and zeros. Quantum computers use qubits, which can be both at once, thanks to superposition. This lets quantum computers explore many possibilities at the same time. Another quantum trick is entanglement, what Einstein called spooky action at a distance. Two entangled qubits are linked, no matter how far apart they are. The math describing entangled particles is strikingly similar to the math for a simple wormhole. This idea, called ER-EPR, suggests a deep link between spacetime geometry and quantum entanglement. Scientists realized they could simulate a wormhole by creating a system of entangled qubits. No need to bend real space. Just program the quantum computer to behave like a wormhole. That's exactly what the researchers set out to do. Let's see how they did it. The scientists used Google's Sycamore quantum processor with 72 qubits. They created two separate quantum systems. Think of them as the two mouths of a wormhole. These systems were entangled, forming a quantum bridge between them. The researchers programmed the qubits to follow the rules of a traversable wormhole. Then, they sent a qubit, a unit of quantum information, through the system. The information didn't travel across the chip. It vanished from one side and reappeared on the other, as if it tunneled through a wormhole. The qubit emerged intact, just as theory predicted. This was the big success, a quantum system behaving like a traversable wormhole. Information went in one side and came out the other, matching the predictions of quantum gravity. It was a beautiful demonstration of theory brought to life in the lab. No spaceships required, just clever code and quantum physics. But was it a real wormhole? Let's be clear. The scientists did not create a real physical wormhole. There was no tunnel in spacetime, no portal to another galaxy, and nothing you could travel through. This was a simulation, like a flight simulator for wormholes. The experiment created a system that behaves according to the same math as a wormhole, but the physical reality is totally different. Information traveled through quantum entanglement, not a physical tunnel. So why is this so cool? Because it's a new way of doing science. The experiment bridges abstract theory and hands-on experimentation. It doesn't mean we're closer to building wormhole spaceships, but it's a breakthrough for understanding the universe's laws. The value is in creating a new tool to explore reality's deepest questions, and that's arguably even more exciting for science. This experiment matters because of what it tested, not what it built. Physics has two great theories, general relativity for the big stuff, quantum mechanics for the small, but they don't work together, especially in extreme places like black holes. uniting them into a theory of quantum gravity, is the holy grail of physics. The wormhole simulation tested a key prediction, that wormholes and quantum entanglement might be two sides of the same coin. This was the first time such an idea was tested in a lab. The experiment showed that quantum computers can be powerful tools for exploring quantum gravity. It's like having a tiny programmable universe to test wild ideas. We can't visit black holes, but we can simulate them and see what happens. This opens up a new way to investigate the universe's biggest mysteries, and it all started with a simulated wormhole. Whenever a story like this comes out, it's easy for the details to get mixed up. First, no physical portal was created. This was a simulation on a quantum computer. Nothing physically traveled from one point to another, just information, through quantum entanglement. Second, quantum entanglement doesn't mean faster than light travel or communication. You still need a regular signal to confirm what happened, and that can't go faster than light. Third, this experiment doesn't prove wormholes are real. It shows a quantum system can behave like a theoretical wormhole supporting the ER-EPR idea, but we still have no evidence of real wormholes in the cosmos. Finally, this was a baby wormhole, just a handful of qubits and a single bit of information. It's a tiny first step, like the Wright brothers' first flight. Not practical travel, but proof that simulation is possible, and that's a huge leap for science. This simulation is just the beginning. Now scientists can build on it. Using more powerful quantum computers and more qubits, they'll create more complex, realistic simulations of wormholes and black holes. Researchers can test what happens if you send more information, or disturb the wormhole. This feedback loop between theory and experiment will push both fields forward. Simulating quantum gravity also drives the development of better quantum computers. The quest to understand the universe is helping advance technology in medicine, materials, and AI. Ultimately, the dream is to simulate the inside of a black hole or the first moments of the Big Bang. By creating quantum analogs of these extremes, we might glimpse new physics. This first experiment has shown us the way. What does this mean for us? It means we live in an exciting time for science. We're witnessing the birth of a new tool for exploring the universe, not just with telescopes, but with quantum computers. Science is a creative process, connecting the largest structures in the universe to the smallest quantum phenomena. It encourages us to stay curious and ask big questions, even if the answers seem out of reach. We use simulations to understand complex systems, from weather to medicine. This quantum wormhole is the ultimate simulation, a model of space-time itself. With enough ingenuity, we can shrink the cosmos down to a size we can study in a lab. The next time you see a wormhole in a movie, think of the real science it inspired. This experiment didn't give us a shortcut to another galaxy, but it gave us a new window into reality's laws. The adventure is just getting started.